Welcome back to Partial Differential Equations. I'm Dr. Jeff Groh. Today we're going to talk about polar coordinates in R2. And in particular, we'll be looking at things like the Laplacian equal to 0, or the wave equation. And these are all dependent upon our calculation of the Laplacian. Using some very simple means, we can convert the usual rectangular Laplacian to a polar coordinate Laplacian. We'll begin by looking at this equation, and in particular we'll have boundary data on some disk of radius a. We'll assume that u, evaluated at r equals a, theta will take on some value u bar of theta, and we'll assume that this u bar is 2 pi periodic. We'll begin our analysis with a separability condition. U is going to have the form of r, which is a function of little r, and theta, which is a function of theta. If this is the case, plugging this into our differential equation, we'll get two derivatives on r, none on theta on the first term, a derivative on r, and then 1 over r squared r theta prime prime. We'll divide everything in sight by r theta, and maybe even multiply both sides by r squared. And this allows us then to separate variables by moving one term here to the other side. Keeping in mind that our solution has to be 2 pi periodic at the boundary, this must be a function which is 2 pi periodic. We'll set this equal then to some lambda squared. So we have the differential equation, which implies then that theta is of the form C1 cosine lambda theta plus C2 sine lambda theta. But again, using the fact that we're 2 pi periodic, that implies that lambda must in fact be an element of the set of natural numbers. Let's suppose we set then lambda equal to n, so that we'll have cosine of n theta, sine of n theta. That gives us then the differential equation r double prime plus 1 over r prime equals n squared over r squared r. Multiplying through, we can move this term to the other side and set this equal to 0, yielding this equation here. We have then something called an Euler equidimensional equation, which has a well-known class of solutions. This is true when n is an element of the set of natural numbers. If n happens to be 0, you have this. However, you can see that this is not physical. And nor is this. Those terms are not physical because they give you singularities as r goes to 0. The solution must be continuous and bounded at r equals 0. And so that preserves only this one solution. We have then, as our solution to these steady-state heat problems, and we can calculate these coefficients an and bn from the boundary data. And this gives us the complete solution to the steady-state temperature problem on a disk. Where our analysis really becomes much more interesting and takes us to an entire new level is when we look at vibrations in a disk. Here, the differential equation will be the wave equation, and we, of course, begin with an assumption of separability. Plugging this into the differential equation, we'll have 1 over c squared t dot dot r theta equals tr prime prime theta plus 1 over r t r prime theta plus 1 over r squared t r theta prime prime. We, of course, divide everything through by tr theta. And we'll try to use separability again. because we're modeling vibrations on a disk, we expect that the solutions to be somewhat periodic. They shouldn't decay away, they shouldn't increase exponentially. And that means we want 1 over c squared t dot dot over t to be minus lambda squared. Minus so that we will get oscillations in t. This equation will be easy for us to solve, so we can defer its solution till later. What's left, then, is minus lambda squared equals r prime prime over r plus 1 over r prime over r plus 1 over r squared theta prime prime over theta. And you can see that we need to get rid of this r squared. So we'll multiply the entire equation through by r squared. Now, in order to separate variables, we'll have to move some terms around. And you can see then we'll have negative theta prime prime over theta equals r squared r prime prime over r plus r prime over r plus lambda squared r squared. Again, because we want a kind of 2 pi periodicity in these solutions at the boundary, we're going to have to set this equal to some constant u squared. This gives us negative theta prime prime over theta is mu squared, and that is also easy to solve. However, to get that 2 pi periodicity, we need mu to be an element of the set of integers. So we'll set mu equal to p for clarity in this case. The final differential equation then will be, if we multiply through by r, we'll move this one over. We'll multiply through by r, and we can divide by r squared. This gives us something called the parametric form of Bessel's equation. The other two ordinary differential equations that we obtained from our assumption of separability were easy to solve. Bessel's equation is going to take a big leap in terms of our ability to solve these sorts of equations. There is a classic maneuver at this point where we change variables, independent variables. We'll set x to be lambda r, in which case the ordinary derivative with respect to x will be 1 over lambda times the ordinary derivative with respect to r. Making this substitution, we'll then have, using primes now as derivatives with respect to x instead of derivatives with respect to r, we'll have Bessel's equation. And it is this equation that we are going to turn to next. Bessel's equation is linear, it is homogeneous, it's second order, but it is not constant coefficient. We have these variables, these functions, instead. In fact, you can see that at x equals 0, we have what is called a singular point. The primary method that you may have learned when you took a course in ordinary differential equations for solving these second-order linear homogeneous problems with singular points is called the method of Frobenius. But the method of Frobenius only applies if the singular point is in fact a regular singular point. The method of Frobenius applies to differential equations of the form y double prime plus some function p of x times y prime plus some function q of x times y equal to 0. X naught is a singular point if p of x and or q of x is not analytic at x naught. So now we know how to identify these singular points and why x equals 0 is a singular point of the Bessel's equation. But what makes a regular singular point? First of all, it has to be a singular point. But we have to find some way to regularize these coefficients p of x and q of x. And in particular, we want x minus x naught p of x and x minus x naught squared q of x to have a removable singularity at x naught. So there can be an analytic version of these. The multiplication by x minus x naught onto the function p cancels out the singularity, and you can smooth it so that it will in fact be non-singular at x naught after multiplication by x minus x naught. Same thing by multiplying x minus x naught quantity squared onto the function q of x. That removes the singularity. In each of these cases, we can then take a limit as x goes to x naught on each of these. And so the assumption of a regular singular point implies that these limits exist. This will be an analytic function, so it will have a finite value as we take the limit as x goes to x naught. We'll call that limit P naught. And Q naught will be the limit as x goes to x naught, x minus x naught quantity squared, Q of x. Both of these limits must exist for a regular singular point. The trick then for the method of Frobenius is to try to find a solution to the differential equation that looks almost analytic. We'll have a portion of this that is analytic. A function is analytic if it can be represented by a power series having a finite radius of convergence. Where we work in the lack of analyticity is by multiplying by x minus x naught to the power r for some value r. R could be some real number. It could be -1, for instance, and that would give you a singularity at x naught. It could be -2 or a -1/2. In this way, the solution is analytic times something that can introduce some non-analyticity. We'll rewrite this as the sum, as n goes from 0 to infinity, of an x minus x naught to the power of n plus r, where r is a real number. Normally, when we take the derivative of a power series, we start at n equals 0. The n equals 0 term would normally be a constant. Its derivative would be 0, so the derivative of the power series would start at n equals 1. But because we have this r here, that's not the case. So y prime will be the sum as n goes from 0 to infinity still. It's going to be n plus r an x minus x naught to the power of n plus r minus 1. How about that second order derivative? We'll need to plug this into the differential equation. So we'll have this sum plus p of x times y prime. But I'm going to take one factor of x minus x naught out so that I can then take a limit later. I've taken this factor out, so I now have a power of n plus r minus 2. And then there's the final term. I need to multiply this final term by x minus x naught squared, so I'm going to have to take two factors of x minus x naught out. And so I'll have to subtract the 2 from here. On each of these three terms, we have this factor of x minus x naught to the power of r minus 2. Which I'll factor out of the whole thing. And for the purposes of our analysis, we'll divide that term off, that factor off. We'll then take the limit as x goes to x naught, in which case most of the terms of this series will go to 0 because of this power. The only one that won't is the n equals 0 term. We'll obtain, let's see, if n is going to 0 is the only term left over, you'll have r plus 1 times a naught. On the next term, if you take the limit as x goes to x naught of this factor out front, you'll get the constant p naught. You'll have left over this r and an a naught. And on the last term, you'll have q naught times a naught. As you can see, this a naught can be factored off, and we get what is called the Indicial Equation. Which restricts the values of r that will give you solutions. In fact, you can see that we'll have a quadratic giving us solutions r1 and r2. It is possible to have r1 equal to r2. But nonetheless, we'll have up to 2 distinct real solutions to the Indicial Equation. We'll then just write down our solution, at least one of our solutions. To the differential equation. You can then use a method called reduction of order to find a second linearly independent solution, or you can try to use the other root of the Indicial Equation to construct a second linearly independent solution and then find the general solution. But let's go back to Bessel's equation now. What are P naught, Q naught, what is the Indicial Equation, and then how can we use that to construct solutions to the differential equation? P naught, since we have x naught equal to 0, it'll be the limit as x goes to 0 of x times 1 over x, yielding a value of 1. Q naught is the limit as x goes to 0, x squared times our function q yielding minus p squared. It follows then that the Indicial Equation for Bessel's equation, and I accidentally had a plus here instead of a minus, is the following, which simplifies a little further because we'll have an r squared minus r plus r. We'll just have r squared minus p squared. That gives us two solutions, p and minus p. We'll have then a solution perhaps of the form, the sum as n goes from 0 to infinity, an x to the power of n plus p, using the plus p for our first attempt at a solution. Going back to Bessel's equation itself, we can rewrite this by multiplying through by x squared. Yielding a slightly simpler equation to work with when it comes to our power series representation. We'll have to plug in the derivatives. And again, we'll do this as generally as possible not knowing the exact value of p, just that it's a natural number, it could be as high as 2, in which case we'll still start at 0 here. We'll then plug in here, we'll add 2 factors of x. That'll bump this up to an n plus p. 1 factor of x, we'll get an n plus p. Over here we'll have these 2 separate terms. One of them will be n plus p and the other one n plus p plus 2. So following through, we'll have 0 as the sum, and go from 0 to infinity. We'll have this term with an x to the power of n plus p. The next one is multiplied by x, so we'll have power of n plus p added onto this. And then with the minus p squared, we'll have the following. N plus p minus 1, plus n plus p minus p squared, all times a sub n x to the n plus p. And then we'll have this last term, x squared times y and in order to then find a recursion relation to solve for the coefficients, we'll have to reindex this last sum. However, there is one thing that we can do now. We can factor out an x to the power of p, which belongs to all of these terms. And we can cancel that factor off. In order to be able to equate the coefficients, we have to have the same power, x to the n, on both of these series. But to do that, we'll have to get rid of 2 here. So we'll have to have a new n, which is the old n plus 2. So if the old n starts at 0, the new n is going to have to start at 2. We can now equate coefficients. We'll have, let's see, n plus p quantity squared. We'll have a minus n plus p and a plus n plus p, and then a minus p squared. This obviously factors as a difference of squares. And we end up with n times n plus 2p. We have then the recurrence relation, which applies when n is greater than or equal to 2. We still have to account for the other 2 terms in the sums, n equals 0 and n equals 1. In the n equals 0 case, we get the tautology 0 equals 0. In the n equals 1 case, we get 1 plus p squared minus p squared, a1. And this implies then a1 is 0, a0 is arbitrary from the first equation. All other coefficients will be determined by the recurrence relation. Since this gives you a kind of every other one principle, a coefficient is determined not by the previous one, but by 2 back in the sequence. And since a1 is 0, that implies a3 is 0 and a5 is 0. A sub odd will be 0. Only the even coefficients will survive. So now let's look at what happens, say, with n equals 2. We'll have negative a0 divided by 2 squared times p plus 1. Now for n equals 4. It's minus a2 over 4 times 4 plus 2p. But a2 is negative a0 over 2 squared. We'll have a positive a0. We'll have a 2 that can come out of here times this 2 squared. That's 2 cubed times 2 squared. 2 to the 5th. We'll have a p plus 2 and a p plus 1. Now for n equals 6, we'll get a minus a0. We'll have 6 times 6 plus 2p. We'll have this, we can write this as 4 times 2 cubed, p plus 2, p plus 1. And let's simplify that as much as possible. We can write this by factoring another 2 out here. We'll have 2 to the 4. We'll have 6 times 4. We'll have p plus 3, p plus 2, p plus 1. And are we seeing a pattern yet? Products of evens can be made into a factorial. We'll have to take a 2 from each of these and maybe leave one of the 2's here. We can think of this as 2 times 3, 2 times 2, 2 times 1, and we'll have a 2 to the power 3 left over. So we'll have an extra factor of 2 from each of those. We'll have a 2 to the 6th, but we'll have a 3 times 2 times 1, 3 factorial. And it's becoming clear. We have these even coefficients. We'll have negative 1 to the k a0 on the top. We'll have a k factorial, a 2 to the power of 2k, and this last part is a gamma function. Gamma of k plus p plus 1. You might recall that the gamma function extends the factorial over to numbers that are not integers, but perhaps real. And so by definition, the gamma function is given by this integral. There's a simple theorem, x gamma of x is gamma of x plus 1. Gamma of 1 is 1, so gamma of n plus 1 ends up being n factorial. You might also be aware that gamma of 1/2 ends up being the square root of pi. However, the gamma function extends this factorial notion to other values as well. In this case, p ends up being a natural number, so it won't be much of an extension in this case. Our solution then to Bessel's equation is the sum. N goes from 0 to infinity. We'll have negative 1 to the k. The a naught can be factored out of the whole thing. That's just going to be a constant. We'll have k factorial gamma of k plus p plus 1. I'm going to take this 2 to the 2k and combine it with my x to the 2k and write that as x over 2 to the power of 2k. This is, by definition, the Bessel's function of order p. Note that it is an even function because of the power of 2. We can allow this p to be real numbers. It can be 1/2, it can be, any number greater than 0. We have to be careful with the gamma function. It's not defined on negative integers. And so that's the only caveat. In particular, if p is a natural number, we'll have the sum. N goes from 0 to infinity. K goes from 0 to infinity. Negative 1 to the k. K plus n factorial x over 2 to the power of 2k. We can plot these Bessel's functions. Here I've plotted the Bessel's j function of the first kind with p equals 1. And you can see that it starts at the origin and it crosses the axis an infinite number of times. We can plot multiple of these together. And the colors are difficult to see. So I'll make them all black. And you can see that these all have a very similar shape, all starting at the origin, oscillating an infinite number of times with decreasing amplitudes. And yet, this will cross the x-axis an infinite number of times. Let's add in something of p equals 1/2. And this will also come down through the origin. Let's throw in one more. The Bessel's function of the first kind, order 0 here, p equals 0, because this one is different. The p equals 0 case crosses through the at a height of 1 when x equals 0, making it a little bit different from these others. As we've just seen, these Bessel's j functions typically start at the origin, j1 half, j1, except for the p equals 0 case, which has a height of 1 at x equals 0. So that's the odd one out. For each p, we truly expect there to be two linearly independent solutions, and we've only constructed Bessel's J function, one linearly independent function. In constructing this, we assumed then that p was greater than 0. There was also the negative p option. So there's an obvious choice for a second linearly independent solution, and in fact, it is. So long as p is not an integer, at least, we'll be able to generate these, because the gamma function is not defined for the negative values of the integers. However, there is another function that can be constructed as a linear combination of these two. It's called the Bessel's y. The Bessel's y function is the cotangent of p pi jp of x minus the cosecant p pi of j minus p of x. And this is also linearly independent from the Bessel's j function, jp. The advantage of the Bessel's y is that if p is an element of the set of integers, we can set yp to be the limit as q goes to p of these yq's, obtaining a solution even for p an element of the set of integers. We have then the general solution to Bessel's equation Bessel's functions satisfy certain identities. First, if you take the derivative of x to the p, jp of x, you'll get x to the p, j, p minus 1 of x. And that occurs for p greater than or equal to 0. Similarly, what happens if it's x to the minus p that you're taking the derivative of times the Bessel's j function? In this case, you get minus x to the p, j, p plus 1 of x, again, for p greater than 0. It follows immediately from the first identity that x times jp prime plus p times jp of x is equal to x times j p minus 1 of x. Similarly, from the second equation, we can immediately write down Oops. And we'll have to have a negative in here. It follows immediately by adding the identities in 3 and 4. Identity 5. You can see that these would cancel. We'd have these two. We're canceling the x off. So we'll have j p minus 1 of x minus j p plus 1 of x. Similarly, by subtracting these can drop out. We'll get double. We'll divide the x off, and we'll have these two subtracted negative. There. Integrating the first identity, if you integrate a derivative, it just undoes itself. We'll have and then integrating the second identity, we have this. We're now going to construct something called Bessel's series. We're going to do this using something similar to what we did, say, with the sine and cosines. If we want to collect a bunch of linearly independent functions of the form sine of some constant times x, we looked for roots, and we found that lambda be of the form n times pi. And so we could collect a whole bunch of these, sine of pi x, sine of 2 pi x, to yield a collection that ended up being linearly independent, and from which we could then construct solutions to our Fourier series problems for differential equations. We're going to do something here that is quite similar with respect to these Bessel's functions. We're going to look for where these Bessel's functions equals 0, and as you know, these things are going to cross the axis a bunch of different times. Let's call this first one alpha p1. The second place that crosses will be alpha p2, and so on. And we won't have an analytic way of expressing these other than these are the first root, second root, and so on of the Bessel's j function of order p. You'll remember that we're on a little interval from 0 to a when it comes to our disk on which we're solving Bessel's equation. So we're going to look at the following sorts of functions. As you can see, this will give us a large class of functions that we can work with. Question is, are these linearly independent? Are they orthogonal in some sense? Can we use them to construct solutions to our partial differential equations? The answer to these questions will all be yes. Instead of using the usual inner product for Fourier series, we'll have to use something called a weighted inner product times a weight x. This is our weight. And one way to think about this, when you're integrating in polar coordinates, you have an element of area equal to r dr d theta. This is like your r dr, if you will. Our theorem will be that if we have, say, alpha pj over ax, that's going to be orthogonal to the Bessel's j function of order p alpha pk over ax, provided j is not k, provided they're distinct. But what happens if they are the same? In this case, this will be equal to a squared over 2 p plus 1 squared alpha pj. This theorem allows us to take an arbitrary function and express it as a series involving these Bessel's j functions. We'll be able to construct these Bessel series coefficients then, just taking the inner product, you'll have a squared over 2 jp plus 1 squared evaluated at alpha pj, allowing us then to solve for these Bessel's coefficients. And the theorem is that if f is piecewise smooth on the interval from 0 to a, then f has a Bessel series representation of order p on the interval from 0 to a. Just as for Fourier series, we're talking about only piecewise smooth functions here, which allows for jump discontinuities. The value that you get from the Bessel series expansion at the jump discontinuity will be the average of the endpoints. So nothing new compared to from before. One can also check that these are solutions to the parametric form of Bessel's equation, provided lambda are alpha pj over a. There are some things that we blew by that we need to check. In particular, the orthogonality of these various pieces of Bessel's j function. We'll begin by noting that Bessel's equation itself can be expressed in the following form: x, y prime quantity primed equals minus lambda squared x squared minus p squared y divided by x. And keep in mind, we're assuming here that lambda is alpha bj over a. And we'll abbreviate this by lambda j, just for sake of brevity. Plugging in our Bessel's functions, we have this equation. For sake of brevity, we'll use the notation j sub j instead of all of this stuff here. That'll give us a simpler way to express these things. So I'm going to look at the derivative of j sub k times x times j sub j prime minus j sub j times x times j sub k prime. You can see that we'll get j sub k prime x j sub j prime plus j sub k times x j sub j prime prime minus j sub j times x j sub k prime prime minus j sub j prime times x j sub k prime. And here we get some cancellation going on. And then over here we can use this. We'll have j sub k times minus lambda j squared x squared minus p squared over x times j sub j minus minus j sub j times lambda k squared x squared minus p squared over x j sub k. Now, all the rest of this can be simplified. You can see that the p squared terms will cancel out exactly. We'll be left with x. We'll have a lambda k squared minus lambda j squared, and then the product. It's at this point that we integrate this. We'll have this constant lambda k squared minus lambda j squared factored out. We'll have our weight x. But we're integrating this perfect derivative. And so we'll get the rest of this evaluated between 0 and a. Note, however, that without the derivative here, each of these j's evaluated at a will be then evaluated at a root, and that'll be 0. Similarly, if we evaluate these at 0, we get 0. And since j is not equal to k, we have that these functions are in fact orthogonal. So now we go back to the solution to a vibrating membrane which is where all of this analysis started. Recall minus t dot dot over t c squared equals lambda squared minus theta prime prime over theta is equal to p squared. We had then theta is a simple linear combination of this form because we require these to be 2 pi periodic. P is going to be m in the set of natural numbers, or 0, as the case may be. We then have the parametric form of Bessel's equation. We'll have different roots lambda mn where lambda mn will be alpha mn over a. These get fed back into the differential equation for t. We have finally u is the sum on m and n. We'll start off with the cosine of c lambda mn t times Bessel's j times cosine of m theta plus bmn sine of m theta. That gives you half of the solution, one with cosine here. You now have the one with sine. And then we'll have amn hat giving us then a general solution for a vibrating membrane. Let's see what some of these look like. I'm going to plot some of the animations about the vibrating membrane, circular membrane. As you can see, we first have to solve for some of the roots of the Bessel's J function, Bessel's function of the first kind. I have it initiated at an initial guess of 2, as you can see. This is a graph of that Bessel's J with m equals 0. We chose 0 for the initial value here. We have this root that we can find, this first root, about 2.4. As you can see, I've turned that into my lambda. And we're using this as our lambda because we're assuming that A is 0. And I'm only going to plot one term at a time. So in cylindrical coordinates, we have r, theta, and the z coordinate will be given by the solution to the Bessel's solution to the wave equation, including our Bessel's J function here in the middle. I've chosen lambda times t instead of lambda divided by c times t because we're choosing c to be 1. Now, as you can see in this very simple model, what we get is a vibrating membrane. Flump, flump, flump. It's about as simple a vibrational mode as you can get. If we change m equal to 1, let's see what we get. You can see that the graph here crosses over somewhere slightly less than 4. We're getting a solution of 10, and that's maybe because we're starting in a bad spot. If we start at 4, we'll get that about 3.8 for the root, which we're going to set equal to our lambda down below. And again, we'll have to set m equal to 1. This vibrational mode, as you can see, it's somewhat different. With m equals 1, the membrane has a big lump and a valley that interchange places as this thing vibrates. Notice that we don't have to use the first root. We could go for the second root, which would be somewhere between 6 and 8. So if we try an initial value of about 7, we can then go to a slightly different vibrational mode. And it looks quite similar, but there is a distinction here, a very definite distinction, by using that second root instead of the first root. Let's try m equals 2. The first root is somewhere between 4, perhaps between 5 and 6. So if we try our initial guess closer to 5, we should get the correct first root. Paint that, paste that down here. Again, we're doing m equals 2. And you can see another very different vibrational mode where you have 2 hills and 2 valleys interchanging places. With m equals 3, looks like the first root is somewhere around 6.4. And again, that was m equals 3. Now we have 3 hills and 3 valleys. So you can see that by choosing different roots or different values of m, you can get different solutions. Second root looks like it's pretty close to 10, about 9.8. Combinations of different vibrational modes that we have seen would also give you more complicated vibrational modes. However, these are just simple vibrational modes based upon one root and one value of m. Let's think about this for a little while. What we've done is just assumed a very simple symmetry. We used polar coordinates to rewrite the wave equation. Using our simple notion of separability, we ended up with Bessel's equation governing the spatial part of our solution. Bessel's equation was singular at x equals 0. We had to use the method of Frobenius in order to solve the equation using power series. When we solved Bessel's equation, we came up with these Bessel functions of the first kind and of the second kind. And then we used roots of these Bessel functions to find linearly independent orthogonal collections of functions using a weighted inner product with the weight of x. And using these orthogonal functions, we were then able to pick apart solutions and add them back together, forming general solutions to the wave equation for a circular disk. This is a generalization of what we did before with the regular sines and cosine series from Fourier series. This is also a form of Fourier series, using Bessel's functions instead. We have an orthogonal collection of functions. So this is a generalization of the theory that we developed earlier in the course. I think you can see that this is really kind of beautiful in its own right, but it should also raise in your mind what happens when we're dealing with other coordinate systems. What happens when we try to solve the wave equation in spherical symmetry, or some vibrating ball? What happens when we use cylindrical coordinates in 3 dimensions, or spherical coordinates? Will we get the same functions, Bessel functions, or will we get other classes of special functions? And the answer is we're going to get new classes of special functions for some of these settings. But that's okay, because we now have a well-defined path for solving these problems. And that's the importance of this particular lecture today. You can see it lays the foundation for a lot of what comes later. And this is a really important theory.